The universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light. And I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Well, hello everybody, and welcome to Skytour Livestream. It is your minstrel of the universe, taking on another tour tonight. How are you all doing? It's good to see you here. It started filling up right away. I see lots of people we know. I want to say hi. Renee Cruz was the first one here. She just bolted right into this chat room like no tomorrow. Michael Hedrick's with us. Hey Mike, what's up? Tim F, woohoo! All right. And, of course, we have, let's see, who else? So we got, Isabella's with us. Hey, Izabela. And we have somebody else that was looking. Oh, yeah, Karen Belmont is with us from Minnesota. Don't tell me you have snow, Karen. I don't want to hear it. You know, she doesn't, I'm sure. And Mr. Django is here. How you doing? You're in the south of France today. That's wonderful. I know you told us last time that you were going to be in the south of France. It's nice to know that that's where you are. Awesome. So, I'm here tonight, and we're going to be looking at the most dangerous places in the universe, at least those that we can see here. And one of them is right here, this guy right here. This is known as the Crescent Nebula. And we've looked at it before, but I want you to see it with a different eye tonight. I want you to look at it as a place where there is so much going on, with so much incredible radiation, that if you were anywhere near this nebula right here, you would be shredded by the radiation. It's just terrible. Hello, Stuffy. How are you? Nice to see you. So yeah, I mean, we're having this is really cool. So let me just get our name out here. Hang on a second. So what I try to do is I try to give you the names of everything we're looking at on the screen, and that way we can then actually discuss them, and you'll be able to see them. All right. So if I go, boop, put our name out there. This is the Crescent Nebula. All right. So why is this one of the most dangerous places in the universe? Well, the reason is because that star you're looking at right there, okay, that star, and let me kind of highlight it for you. It's this guy right inside the red square, okay. That star you're looking at is so hot that it's actually heading towards supernova land, and it will be in a condition where it's going to obliterate itself in the future. Now, why would it do that? Well, it would do it because the star is actually very massive and very, very hot. And so what happens is when a star that big gets so hot, its core will be radiating out massive amounts of radiation. And for reasons we don't quite understand, sometimes bursts of radiation will push out of that core at a very, very high rate. And when that happens, it literally pushes the entire outside of the star, what we call the outer envelope, because fusion occurs only in a tiny little ball in the middle of the star. Okay, it pushes that envelope away, and sometimes it's enough to free it entirely from the star, just like we see here. Okay, this is an area that's been freed, from this star. So what we're looking at there, in a sense, is sort of an exposed outer core of the star. And so this part is the gas that was in the envelope. When we look at our sun, it looks like a disk in the sky. But what we're really seeing is a tiny little core, the only place where hydrogen fusion is taking place. And in that tiny core, it's outputting radiation in all directions, okay, towards you, away from you, out the sides, and the front and the back, etc. And its radiation output is so high that it overcomes the gravitational force of such a mass trying to contract it. So it reaches an equilibrium. It's pushing out as hard as it's trying to be pulled in. That's called hydrostatic equilibrium. Big words, but all stars are in a balance like that. Now, in this particular case, something happened, and the star left this hydrostatic equilibrium behind, and it began to push its outer layers out. It overcame the gravity of self-collapse. And again, for reasons we don't quite understand, it did this. So when we look at this, we're looking at what used to be in the disk of the star, if you could see the star as a disk. All right? But now it's spread out several light years from this extremely hot star. Now, why is it so dangerous? Well, not just because of the millions of degrees of temperature that this outer gas has become, but because of the fact that this star is extremely hot, and its radiation that it's putting out is a lot of the ultraviolet radiation that we see from the stars is coming from the fact that the star is so hot. So stars this hot do radiate most of their energy in the ultraviolet spectrum. O stars do, the hottest and bluest of all stars. So well, when we see this star doing that, the interesting thing about these stars is that they are showing us sort of a precursor to what they're going to be. By blowing out these outer layers earlier in their evolution, they will end up blowing out their entire guts in the future in a massive supernova explosion. So that's what this star right here is destined for. Wouldn't that be cool if it happened during our lifetime? Yeah, it would. Because we'd see it now. The Crescent Nebula being some distance away, and I'll get you the numbers here if they're published. It's about 4,700 light years away. Let me just zoom in on it so you can see where it is. This is the Gamma Sygni Nebula, where we're going to go next. So this is in Cygnus the Swan. Okay, and just to see where it is, let's back out. All right, there's Cygnus. Now, how do I know? Because I will show you. Okay, there's the beak and the head of the swan. That's Alberio, the beautiful double star that we always talk about. And then at the center is Sadr, which is the central breast area. And then we have the wings out here and the tail, which is Deneb. Okay? Now, let's hide that and come back. So now you know where we're looking. Now, if you look where the telescope's looking, it's 7:30 out there. Okay, and it's already dark, which means we can start a little earlier now. All right? The thing that's interesting is when you look at the places in the sky where this is right now, at 7:30 at this time of the year, October 22nd, Cygnus, if you look where the telescope's pointing, it's almost directly overhead at 7:30. So we're actually getting the best view. And Tricia Ferreira, I gotta tell you, you are, of course, correct. The most dangerous place in the universe is the Earth. We get that, and you're right. I mean, from a certain perspective, I'd say you're probably correct, and that's okay. Luckily, we have a history of trying to correct our mistakes. I'm not sure if we can, but we will try our best. Renee Cruz says Tabby Star Dyson Sphere. I was investigating Tabby Star. That's Tabitha Bayagian. She's an astronomer, and she discovered a star through the Kepler data that was dimming over the course of a period of time, sometimes by up to 20%. Now, that could have been because a giant artificially created sphere that surrounded that star to capture all of its energy, something that Freeman Dyson came up with, a Dyson sphere, as a thought, a possibility. It could have been what we saw. Now, they thought maybe it was a swarm of comets, then they thought maybe it was dust. And at this point, they think that it was probably a passing dust cloud that was between us and Tabby Star. I prefer to think of it as a sign of extraterrestrial intelligence. You know, that would be kind of cool. A technology signature from a distant star. But we may not have to go that far because we've talked about this before, the James Webb Space Telescope, and we've talked about this on SkyTour Radio on Sunday nights. Tonight we didn't have a show, but we will next week. The James Webb Space Telescope discovered an exoplanet around a star, an M-class star, so not a very big star, kind of a very small star, and it seemed to be what's called a Hycean planet. That is to say, a planet with mostly a Hycean, okay, a hydrogen atmosphere. And a hydrogen atmosphere, but below it seemed to be, from what we can tell so far, is a planet that's made up of a lot of water. So in other words, maybe it's a true water world, like in the Kevin Costner movie Waterworld. I don't know for sure. But the fact is, there could be life there. And you'll say, but wait, what about oxygen? Well, the thing is, there are certain processes and life forms that do not require oxygen. So maybe there's microbes there that are doing this. And the reason that we think that is because of the fact that they found in the signature from this planet a chemical compound called dimethyl sulfide. What's dimethyl sulfide? Well, dimethyl sulfide is obviously two methyl groups, dimethyl, okay, sulfide, sulfur, okay. But keep in mind that dimethyl sulfide is something that you're very familiar with. You just don't realize it, okay. And this dimethyl sulfide compound literally is something known as the smell of the sea. You know, when you go by the ocean and it's low tide, you're like, oh, what's that stink? That stink is dimethyl sulfide. Where does it come from? Well, I'm going to be crude about it, but it's basically plankton flatulence, plankton farts. So, it's possible that there are microbial creatures on this distant planet that are putting out dimethyl sulfide as a waste product, and we're picking it up. So it's possible, think about this, it's possible that the James Webb Space Telescope may have just recently found a true extraterrestrial life form. Maybe a whole planet of them. It's a possibility. Dimethyl sulfide does not come from anything other than life, typically. And especially in these quantities. So I think that if we look at the possibility of dimethyl sulfide being a major component, you just say, well, where does this, where would it come from, and what's the status? How could life form? How would it reside under a hydrogen blanket like that? And the answer is that we don't know yet. Isn't that great? It's so cool. I mean, we don't really know. And I'm okay with that. I don't know about you, but I think that it's really, really important to, keep studying, keep looking. And I guess this is beautiful. I'm going to say this just like this. I've been doing this for a while before you guys came in. I wanted to get a nice photograph of this because I really wanted you to see the area here in the universe that we consider the most dangerous, one of the most dangerous. So all this material that you see here, this is live, by the way. Remember, all this is live. Okay, this is not a photograph that I just stuck on the screen. This is live, right before your eyes, the universe live in real time. That's what I think this is so beautiful about this. Now, we can do some more things here. We can actually squeeze this and compress it to get a little bit more detail. And as I do this, you'll see, and I'll back out a little bit so you can see it better. You can see that there's more than just that there. Okay, because in this region we also have a lot of this red gas, this ionized hydrogen gas. And let's just darken that background so you can see that a little more. So look at that. A lot of ionized hydrogen here. Really, really cool. Michael Hedrick, was the dimethyl sulfide something you want me to talk more about? Because I've just been doing that, so maybe that's what you were asking. Unless he asked. Renee Cruz says the Parker Solar Satellite is so fast that it's breaking past NASA records. Yeah, well, it is orbiting the sun, so it's moving quite fast. I'm not sure if it's the fastest, though. I believe that the New Horizons probe probably takes the record for that. But that's really cool. So let's see here. Hi, Daisy and Zoe. Didn't see you before. Nice to see you. Let's see what else. Renee Cruz is full of great ideas tonight. All these wonderful things she mentions. And Michael Galea is with us. Hello, Michael. Good to see you. Michael Hedrick says, oldest radio burst ever found could tell us what exists between galaxies. That's correct. These galaxies, these signals emit as much energy in milliseconds as the sun does in 3 days. Yeah, let's talk about that, Mike. That's actually a good thing to talk about. Okay, the FRBs, or fast radio bursts, are these massive pulses that come from billions of light years away. Now, how can we tell? How can we tell where they come from? Number one, and number two, what they're passing through. Well, there's a little trick we can use, and first of all, knowing where they're coming from is a little bit easier because we can pick up the radio burst striking the Earth, and we can figure out where it's coming from. That's not a problem. However, one of the things that you might wonder is how can we tell what's between galaxies? I actually covered this, last year in Sky Tour Radio. And, but I'll do it again, I don't mind. So, what happens is, as the light is coming from a fast radio burst, and let's not discuss how they occur, I have ideas which I'll share with you. As the light comes, the light frequencies are affected by the material between galaxies, if there's any material. Some of them are changed, slowed down. Some of them are shifted. And based on what they look like when they arrive, we can tell what they went through to get here. Okay? That quality, that characteristic of these fast radio bursts is called the dispersion. Okay? That's DISPERSION, dispersion. Okay? And what the dispersion looks like will tell us a little bit about what they pass through. In fact, the dispersion of some of these FRBs that we've seen shows that these radio bursts pass through vast quantities of hydrogen gas that's floating out in intergalactic space. Okay, as an example. So it's an interesting science. We can see the light, and then we can see what it's gone through based on what it looks like when it gets here. Because that stuff out there is leaving fingerprints in the spectrum of this material arriving on the Earth. Isn't that cool? So little by little, we're unplugging the secrets of the universe, and but this right here, this is something that's really still a mystery to us. This is called a Wolf-Rayet star. This one right here. Okay, and a Wolf-Rayet star is extremely hot. We've talked about this before. And as they're pushing off their outer layers, what's in that red box, okay, they will eventually go supernova. They are prime supernova candidates. How long? Can't tell you. But this has been moving out for quite a number of years, obviously, to get this far. Maybe 1,000 years, I'm not even sure. Maybe so. So I think that as this happens, okay, the stuff at the beginning of this, let's actually zoom in. Let's say that your world is around this star right here. Okay, and let's say that star is the same, it's going to be hit by this expansion here, this expanding cloud of very, very hot ionized gas. Okay, if that was true, then what would happen is your planet could be damaged severely by this very, very low density layer, but very, very hot material. And on top of it, we also have this star's radiation that's making it out. If this again was nearby, this star is causing this material to be ionized, so it's actually reaching out several light years to do this. Now, as it sends out this gas, all right, as it pushes this gas out, the gas is colliding with other material in the interstellar medium, and that collision can also cause the gas to heat up and can also cause it to ionize. And we could see the characteristic colors of hydrogen and oxygen in that same way from that. Now, as the season wears on here, we will be able to see another one of these Wolf-Rayet star locations, actually two more, and they are not the same color. They're bluish green. And those are going to be where the central star actually blew off mostly oxygen. It depends what the star was made with when it was first made. Okay, so the red is hydrogen gas, right? And then there's areas down here where you see green. That's oxygen, all right? And that could be oxygen that was just free in interstellar space. It doesn't necessarily have to have come from here. Okay, so it doesn't necessarily have to have come from this Wolf-Rayet star. It could have been out in the interstellar medium, and the Wolf-Rayet star itself has radiation. It could have ionized this material. So that's pretty cool. So we'll save this once again. Izabela, you're gonna have fun, because this is a nice image, and I'll tell you, it's just looking really pretty. And if we zoom out, let's try and pull out more detail here. So if we do that, we bring this in and capture more of our data curve. You can see all these red nebula around here. Just beautiful. This guy here, being over 4,700 light years away, is, again, now knowing that it's 4,700 light years away, okay, we can actually then say, well, if we take this photograph, one of the things that we have now available to us to do is we can measure this length right here from here to here, and we can find its exact size in light years. And I wrote a program to do that. Very simple. And for those that are interested, it uses something called the small angle equation. And the number 206265 will be very familiar to you if you know that. And the small angle equation will allow us to calculate how big this is in actual light years, okay, knowing how far away it is. And that can also give us, with analysis, we can also get an idea of how fast this stuff was moving. All right, because it did get blown out from the main star. So that's something that would be very interesting to discover. So I'm going to... All right, I'll do one last save. Okay. All right. And then I will save it exactly as seen. Okay. So now we can come out of here. This is going to be up on the server. It's already up there. Much of it's already up there. All right. And now we'll go back to a night vision mode so we can actually find the next object. There it is. That's that guy. Yeah, let's green your screen. I'm reading some of the let me pop that off. Bink. There we go. Karen, Izabela is all those things. She is a graphics designer and works with imaging programs as well. So she will be processing this as well as I, and I will say as well as I, because she has learned an awful lot, and I'm just really impressed with what she's done. Okay, let's now let's move to the next object right nearby here. Okay. So notice the size of the Crescent Nebula here, and then notice how big this next nebula is here that we're looking at. This guy is massive. This is the central star in Cygnus the Swan, Sadr, and we're going to go there right now. And there's a reason why we're going to it. And that is because Sadr is a supergiant. It's a star near the end of its life. Okay? And it's going to end its life as a supernova. There it is. So when Sadr explodes, again, it's going to be distant. It's not going to hurt us. I'm going to leave it on this side for reasons you'll see in a minute. But I'm going to raise it up a little bit. Okay. All right. Sadr is what's known as an F8, and then Roman numeral 1, and then little letter B. F8 1b. It's a star that is a little more white than our sun, and it's near the OBAF range. And then we have G, which is us, and then K, which is orange, and M, which is red. And Sadr, right here, is an F8 1b, a Roman numeral 1b, and that means it's a supergiant. And it's a supergiant star that has already gone through all of its hydrogen and has swollen up into a red giant. Now, Sadr is also, as a supergiant star, likely on what we call the asymptotic giant branch. What's that mean? It means that when the star uses all its hydrogen, the first thing that happens is the core starts to contract when the hydrogen is no longer there. Gravity's pulling down and the core contracts. But when that happens, it gets very hot. And guess what? It pushes out with a lot of high energy at that point, and that causes the star to bloat really big. And that's when it becomes a red giant for the first time. Then that core, continuing to contract, gets hot enough so that helium can start fusing. So it was going hydrogen into helium, and then now helium into carbon. And when it does that, it's got a new lease on life, and it's able to fuse helium into carbon, and so forth. And now at that point, the star does that for a period of years, okay, maybe a few thousand years, and then it gets a little bluer. It turns more toward the blue end of the spectrum just a bit. And then when it runs out of that, well, then the core begins to contract again because it doesn't have, gravity starts to crush it, and that pushes out with radiation again, and for a second time, the star bloats into this massive red giant, and that's when it comes up along the same path that the last red giant phase had. All right, so at the end of this second red giant phase, the star is going to do one of two things. It's either going to do a core collapse supernova, or it's going to shrink back down and become a potential white dwarf. It depends on its mass. All right, most likely it's going to end up exploding in a supernova. And boy, oh boy, wouldn't you want to see that? Our sun could never do it. It's not massive enough. And there's no stars near us that are dangerous for us right now. None. So, one thing we want to consider is that if this star was to go supernova, that we would end up, of course, wanting to see it. And all we'd have to do, if it happened now, we just look up. We go outside at night. And Sadr is a star that is 241 light years away. So it's actually quite close to us. It's actually not really that far away, but it's well past the location where a star that blows up can hurt us. Okay, 30 light years or so, maybe 50 light years, depending on the mass of the star, could be hurtful to us. But beyond that, no. So let's now that we're guiding here, and it looks like we're guiding well, we're going to go up here and do a nice 25-second shot. Okay, that says 35, doesn't it? Okay, 25,000 milliseconds. All right, and that's going to be for our Sadr complex. Now, this is Sadr, and over here is a vast nebula. That nebula is not being illuminated by Sadr. The nebula is several thousand light years further away. Okay, that's our old one, the Crescent. Now, keep in mind, we do have a just about first quarter moon, just past first quarter moon out. So our sky is a little bright. If you were there in person, you probably wouldn't be able to see the Milky Way too easily. Okay, but that is why we see this blue haze in here that we see now. All right. So that said, let us do a color correction first. All right. So there we go. Color correct, and then we will do a correction for our data, and zoom out on our data just a bit. There we go. So look at that. So now you see this beautiful red nebula. This is actually ionized hydrogen once again. Hydrogen is the most plentiful element in the entire universe, and it's a very simple element. It's a proton with an electron cloud in it. Okay? Now, we were taught, as you were all taught probably in grade school and beyond, that a proton is a particle in the middle of the nucleus for hydrogen, and the electron is another particle spinning around it. Well, the truth is actually stranger than fiction. The electron isn't really a particle, and the next thing I say is going to really be confusing, but the electron is actually a probability. It's not a particle. P words, but different. And you have to look at certain principles, like what's called the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle says that you can never know exactly where an electron is at any one time, effectively. And so, because of that, we notice that the electron is somewhere around the nucleus, and it's in what has been termed a cloud, an electron cloud. And when you say, is it here or is it there? Okay, you say it's in both places. Wait, what? Yeah, it's in both places. So our understanding of quantum physics is basically just a little bit complicated, and so that's something that I think any extraterrestrial species is going to have to figure out and know all the ins and outs and nuances. I mentioned this last time, but one of the lectures I'm doing around the country now, I'm doing one this Wednesday, and I'm doing one this Saturday on this. And Wednesday I'll be at the Plainville Public Library, where I grew up in Plainville, Connecticut, and there's some local papers doing news stories on it and everything. I'll be there as a History Channel whatever guy, and I'm going to be talking about some of the quantum physics properties, but in lay terms. I mean, it's hard to talk about physics at a lay level, isn't it? Because there's so much background you got to know. But what if I told you that you didn't have to know all that stuff? What if I told you that all you have to do is accept a few little factoids, and then from there you can leapfrog into a full-blown understanding of how an alien species from, say, this star here that might be, say, 150 light years away could be here on Earth now, right? And so I talk about the principles under which this could happen, and it's a look at some new physics, and it's something that is, well, I say new physics, it's a fresh look at old physics, okay? And so it has to do with specific particles and usage of specific particles, which, by the way, CERN overseas is at the Large Hadron Collider, is exploring, because these particular particles that I'm referencing here, without naming them at the moment, have turned out to be quite interesting for reasons that, reasons I lecture. Okay? And Lawrence Livermore Laboratories, on the other hand, is developing a potential fusion reactor. Wow, fusion reactors. Hello, Ronald. A fusion reactor is very important because to create those particles I was telling you about that allow them to basically slip through space interdimensionally, which is what this is, you just need a fusion reactor. So Lawrence Livermore is doing something over there, and CERN's doing something over there, and both of those are going to get married in the middle and produce potentially the first interstellar probe from the human race. And we'll probably go to Alpha Centauri. Probably go to Proxima first. Now, at the way this works, we might be able to get to Proxima in just a few hours. Now, that's a darn sight better than the than the 10,000 years at the fastest possible speed we've ever gone, right? Hello, Sam S. You know, but it's also not a impossibility. And if we look at this advanced physics that we're talking about, this advanced physics is something that would allow us to travel interdimensionally, because we're in 4 dimensions, X, Y, and Z, all moving through time. Pinky is time. Okay, so when I'm over here, we've gone X, Y, and Z and moved through some amount of time. Move over here, and I've gone to a different X, Y, and Z coordinate at a different time. But what if I told you can go into a 5th dimension too over here? This 5th dimension is interesting because once you enter that 5th dimension, the universe around you can become compressed. So everything is closer to you. Everything is more compact. And the farther in you go, the more compressed it is. So that means that the farther in you go, you could actually jump much further the farther in you go. If you go in just a little bit, then you could go to different places, say on the Earth. Okay? You could go 5 feet ahead of where you just were, endlessly, and to any technology on Earth, it would look like it's something moving in a straight line. Or you could go 5 light years in one shot, because you're not really traveling the intervening distance like we're doing now, because we're constrained to the 4 dimensions. If we can get into that 5th dimension, okay, that's truly like hitchhiking to the universe, isn't it? Right? Age of Aquarius, 5th dimension. There you go. This is the dawning of the age. Oh, I don't want to get that stuck in my head. Thanks, Trisha. That's cool. So the bottom line is that if we look at the different amounts and different capabilities that we might have, it's possible that we're looking at a future where we will be able to go interstellar and use this 5th dimensional travel. Now, this isn't a Mark D'Antonio thing. This is actually a Bob Schroeder thing. Bob Schroeder, aeronautical engineer, physicist, okay, and other physicists in the country and astrophysicists are on board with this. In fact, here's a little secret. This is why I think CERN is investigating these particles, because these particles to them are very fascinating. Why? Well, they have some pretty cool qualities, like I mentioned. And these particles are known as Kaluza-Klein particles. That's Kaluza and Klein, Klein. Kaluza-Klein. And if you look up Kaluza-Klein particles and then put the next word in your Google search, CERN, C-E-R-N, you'll find a white paper on the CERN website all about Kaluza-Klein particles and reference to the new accelerator they're building to, in part, study these particles and their very fascinating capabilities. We're on the precipice, in a way, with going interstellar, and none of it has to do with anything we've actually explored before. We've talked in the past about the Alcubierre drive, right? That's a warp drive where you have a space between A and B here, and if you can fold space and fold up the corners together, step across that little gap, and then unfold space, now you're there without crossing through the intervening space. That is the warp drive, and that required so much power. So much. Oh, Izabela found the paper. Excellent. Thank you. It requires so much power to make that warp bubble, to make that warp jump, that it's kind of impractical. However, to do the jump we're talking about interdimensionally into this 5th dimension, you just need the power of a fusion reactor. Hey, that's Lawrence Livermore, like we talked about. So they're developing a fusion reactor. Now, they did a successful test, as I mentioned hundreds of times, I think, to you. And just shut me up if you've heard it. They've done this amazing test where they actually found that the reaction could be sustained in a fusion chamber. They were able to sustain the reaction. That's kind of hard because stars like this one, okay, that are doing fusion, their temperatures in their cores are in excess of 100 million Kelvin. It's really, really hot in there. And if you're just doing hydrogen fusion, it's 13 million Kelvin. All right? We don't have anything that can contain something that is going that hot. All right? So that said, the achievement that CERN, that Lawrence Livermore pulled off, was that they could create a sustained reaction. That was the big problem, a sustained reaction. And the other problem is getting more energy out than you put in. They haven't done that yet. That's called the break-even point. We're not at that. I don't even want to even imply that we are, because we're not. But the break-even point is something that is an ultimate goal. And when we get to that break-even point, then we're going to have the ability to create the fusion reactor and tie it to Kaluza-Klein particles and use it to create these special gravitons that we surround our little ship with. And those Kaluza-Klein gravitons live in that fifth dimension I was telling you about. And our ship will get pulled into the fifth dimension automatically because they're shrouded with these gravitons. These gravitons also create micro black holes, which do exist, theoretically. And these micro black holes, they only live a few nanoseconds. Okay, they come into existence and they're like popping soap suds. They're gone within a fraction of a second, because that's how they operate. But if you keep supplying the soap suds, then you can have soap suds around your ship the whole time. Okay, and that's what those micro black holes would be. And what those micro black holes do for you is they create the possibility for your ship to not feel the Earth's gravity. Why is that? Because micro black holes, they pull in a little light, maybe a molecule or two of the atmosphere before they're gone, and then they actually also absorb the gravitons coming from the Earth that are holding it down. In other words, the Earth's gravity can't reach the ship, so it just sort of flutters freely like this, not even subject to a gravitational field. See? So the micro black holes, which live in the fifth dimension, would then cause the light to be bent, distorted, change colors on you. It might look like it's popping in and out of visibility. It might look like it's going from one spot to another in the sky instantly. All possible, because most likely they're bouncing back and forth, going into that fifth dimension and back into our four dimensions, back and forth like on a cycle. It's probably like a motor. It's going to work like that, ding, 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 ding. And the whole time it's doing that, they either go further, very small jumps to go very short distances on our planet, or long jumps to go longer places, and farther places. So that kind of thing, this is coming up beautiful, by the way. So that kind of thing is really something that is actually a distant possibility now. This was science fiction, a couple years ago. But with Lawrence Livermore's findings and with CERN investigating these particles, it's not so much science fiction anymore. Now, it depends on string theory being factual. Now, string theory is a whole other way to think about physics. And remember I talked about the proton and the electron? Okay, now I'm going to make you think about something totally different. So imagine a proton, right? Think of it as a single particle sitting right in the middle of the hydrogen atom. Pink, there it is. Well, that proton isn't sitting still. That proton has energy. It's going back and forth. It's vibrating. Okay? Now, that vibration that you see there never stops. It never ceases. So what if you could say, stop the proton there and there at both ends of its travel and its vibration. So it's going like this. You can't even see it, but then you slow it down, and then you stop it here, mark that position, stop it here, mark that position. And what's in between? What's in between is the path it took to go from one position to the other, right? That's the string. Think of that as the string. So it's the energy, okay, that's in between that vibration. Now, I ask you to think of it that way so you can see a visual aid for what string theory is. And if you think of the universe in that term, that opens up a whole new branch of capabilities that we can't access with our current standard model of physics. And that's the thing that is so darn cool. And that's why the fifth dimension could exist. Okay, and the fifth dimension could be a place where we could go, and the more we go in, the more it's actually a very warped dimension. So much so that it would actually allow us to be in both the fifth dimension and our four dimensions here simultaneously, and we'd be vibrating back and forth between them. This is why, and that reason right there is why, for instance, when you see you hear a story about a UFO traveling through the sky, it seems to be moving at an unbelievable speed, and it doesn't seem that the UFO is subject to the air. It doesn't seem like anything's happening. It seems like it's not being slowed down. It doesn't leave a vapor trail behind it. It doesn't make a sonic boom. What's going on? Well, the reason is because it's in the four dimensions so that you can see it. But then it's constantly shifting to the fifth dimension. And it's coming back. It's probably a computerized process with some advanced computational system. And it goes in just a little bit. And then when it comes back out, it punches back into the four dimensions just slightly ahead of where it was. This means that the ships don't even require propulsion. They just need to be able to wink out and wink back in, punch out and punch in. And that punch in process, that punch out and punch in process, is one that is just in requirement, needs a fusion reactor. And a fusion reactor will be in a ring, just like our cyclotrons and our accelerators are now, okay, like the Large Hadron Collider. And in a UFO, UFOs have traditionally been round or triangular. And that's because I think they're particle accelerators. Dispensing these particles around their outside, sheathing them, and keeping the central core protected from any dangerous radiation like synchrotron radiation, which is generated when you try to keep particles moving in a curved field with a magnetic field. So there's an awful lot to think about there, you know. So that said, that was just sort of a little treatise. We started by looking at Sadr here, and by talking about Sadr, we're mentioning that because Sadr being 270 or so light years away from us would be a hop, skip, and a jump for such a propulsion system, for such a punch-in, punch-out system. We could go to Sadr, check it out. We could go to Alpha Centauri for lunch, no lie. Now, I know that sounds crazy, but we have a couple hundred years of work to do before we can get to this, most likely. We have to go through our fusion research. We have to go into the fusion reactor arena. We have to have fusion reactors running for 50 to 100 years and giving power to many households around the world before we would probably go elsewhere with this. You know? So let me look at some of the questions in the chat here, because I've been going on and on. Let's see here. Ronald said, what is the maximum speed needed to acquire the bubble theory? I think you're talking about the Alcubierre drive. It's not the maximum speed. It's the maximum energy. Okay, and we kind of know that because Miguel Alcubierre, who came up with this concept in 1994, calculated initially that the energy required to make the warp field, to warp space and bend it, like I said, and cross between the 2 points, and then unfold space, the energy required would be on the equivalent of converting the entire mass of Jupiter to energy. So that is a colossal amount of energy, and that's just to do it once. How are you going to do that multiple times? So, to understand where that energy comes from and how we figure it out, all you have to do is go to Einstein. He had a famous equation called the mass energy equivalence equation, and you know it. It's E equals mc squared. Notice on one side you have the mass, m, and the other side you have energy, E. Well, they're related to each other by the speed of light squared. So that's the mass energy equivalence. That's how that works, see? So you take the mass of Jupiter, plug it in there, multiply it times the square of the speed of light, and that gives you the amount of energy required to make this warp bubble. Okay, that's what he discovered. But in later years, other scientists and folks like Sonny White at EagleWorks Laboratories came up with a different approach. And they figured, hey, we might be able to do this by just changing the geometry of our spacecraft. And by changing the geometry of the spacecraft, he discovered that he could knock the requirement down by like 10 to the 26th power. Now that meant going from having to convert an object like that's the mass of Jupiter to energy to an object that's the size of the Voyager spacecraft or so, and converting that to energy. That is an incredible difference, and it actually made it something that might be plausible. So the Alcubierre drive, maybe we'd use that for solar system travel. The dimensional drive, maybe we'd use that for interstellar travel, right? But when we talk about going intergalactic, well, we really, really need to be able to understand how all this works to be able to do that very well. I don't think we'd go intergalactic. I think there's plenty of life within each isolated island universe, as I call them, which is what each galaxy is. And here in this image, we're looking from within our galaxy through dark dust clouds right here. These are dark dust clouds we're seeing here. Let's highlight them here. Let me bring them in at the risk of everything turning a little more blue. You'll see them. Okay. Now we just drop this in. Okay. So this is that diffuse hydrogen cloud out here, and it's all mixed with dark dust. See the dust? That's not a hole where there's no stars. That's actually a dark dust cloud that's between us and the nebula behind it out here. All right. Same with this. This is a dark dust cloud in the foreground. All right. And we can tell that by looking at the material, looking at the extinction of starlight that's being dimmed by this dust, in other words, and more. All right. But this is a beautiful nebula, the Gamma Cygni Nebula. And I'm really pretty sure that this star here, I know for a fact this star here is not doing any of the lighting up. That's a foreground star out here, and nebula's way, way out here. The nebula's approximately between 2,000 and 4,000 light years away, I think, and we can figure that out. And then this here is only 240 light years away or so, 270. So let's go in here. Let's bring it back in. Okay, and Sadr is distance looks like 241.3 light years. That's how far away it is. All right. So that's interesting. All right. Now let's see here. And then Gamma Cygni Nebula here. This is cool. Okay, the Gamma Cygni Nebula. Yeah, see, Sadr is 200 and however many I say, 215. Why am I forgetting that number? 241. Yeah, and then the Gamma Cygni Nebula, the part behind it, is over 800, almost 900 light years away. So this star is not affecting it. Izabela says, Mark, just one more question. Do Do you think string theory can explain entangled particles, the information traveling in 5D, and for this seems instantaneous to us? Actually, string theory and entanglement could very well be linked together, yes. And let me just explain entanglement to those that are always been confused by it. It really isn't that big a deal. It's called spooky action at a distance. Okay, that's what it was termed. But let's say you have a material and you split it in half, and you take one part of it and you move it into lab A, and you take the next part and you move it into lab B, and make lab B on the moon and lab A is on the Earth. You look at the electrons in, say, one set of atoms in lab A's sample, and you check their quality called spin. Electrons have different characteristics. One of them is spin. It's up or it's down. And if you measure those and you see that they're spin up, then you don't have to check the Earth's version from the moon, because the Earth's version will be down, spin down. Now, how do you know that? Because there's a strange communication going on between particles at a distance, and it appears that it doesn't matter how far away. Now, when you look at the following, if you were to change the spin of the electrons you're looking at from down to up, then the electrons on the Earth will instantly change from up to down, because they have to be opposite. Okay, so it's really interesting how this works. And now the fact that this happens, this is what's called quantum entanglement. At some quantum level, these particles are actually connected, entangled. That's where that comes from. So could they be contained or entangled through a fifth dimension? Maybe. Don't know. Nobody really does. That's why Einstein called it spooky. It's spooky action. Ronald says, what happens if something is messed up? Well, that's a loaded question. We get stuck somewhere in the other dimension. Well, you got to be careful, Ronald, because that fifth dimension is a dangerous place. And if we're not producing particles properly, we won't be protected by that sheath. As long as we have them, we're protected in the fifth dimension. But if we don't maintain the production of the particles, then we could be in deep trouble, and our ship would get instantly crushed out of existence. So, you want to go yet? Huh? Come on, you want to go? I'd still try it. Just once, So there we go. So this is the Gamma Sygni Nebula. Okay, and let me rename it here. Okay. And we'll say save. And save exactly as seen. Okay. And there we go. Alright, so now let's go check out something else. I want to go down here to the actual Gamma Sygni Nebula and check that out, because that's got a really interesting look to it as well. I gotta go back to my here we go. We're drawing Etch-a-Sketch pictures on the sky. Alright. Alright, there we go. Let's okay, now we're searching. It's gonna take about 14 seconds for us to get our guide star up here. Cosmic Ray, the movie The Fly, was the original one was pretty good. The remake was okay. That was Jeffrey Goldblum, right? Wasn't he in that? I think he was. Okay. So we're up and running here. So now let's do this. Yeah, Daryl's not with us tonight, Ronald. Okay, so let's go 25 seconds. And then we'll come out and go into our live stack, and you'll see our remaining image from the last buffer. That will probably make a really pretty image. We have a way of getting rid of all these halos now, so that's great. Okay, so now let's take a look at this nebula. It's probably just a little bit down there. Okay. Let me bring that back up. Okay. I'll bring this up here. All right. For those that may remember, we had Ronald, ERT Radio, on with us the other night. He's one of our top Patreon subscribers, and he got a tour of the night sky with all of you and ended up getting some imagery of the double cluster and the Andromeda galaxy, I believe. And we threw in a couple other things for him too. And we have them processed for him. And he'll be getting copies of those as our Patreon, upper Patreon subscriber. Okay, now. Okay, we're now guiding. Let's do this. Let's go to 25 seconds again. And live stack this one. There we are, and we'll clear this. Now we brought this up here more. Hello, Cindy. Cindy Murphy's here. There we go. Alright, that's actually the Gamma Sygni Nebula, the classic Gamma Sygni Nebula. Okay. Just adjust this a little bit. So the reason I'm taking this for you guys is to show you the mixture of the dark nebula, which is all throughout here. This is not an isolated hydrogen cloud out in space. This is an area where there's less dark dust around it, and it's actually showing through. Pretty interesting, huh? Okay. Let that develop. We have 3 that have been taken now. This is actually a very pretty nebula when processed. And some of the subtle features are going to come out here in just a little bit. Sam S says, isn't the 5th dimension an extra dimension is extremely tiny? Yes, exactly. They are. And you're thinking, well, how can we get in there? Well, because our ship is going in there basically an atom at a time. Renee Cruz says spooky molder. No one gets to help me, and it's actually help me, help me. That's from the Fly movie, the original. Remember that? So I got it, Karen Belmont. Yeah. Okay. You didn't miss the email for your galaxy picture, Ronald. I didn't send it to you yet. You'll get a message saying that it's coming in a Dropbox. Alright. Alright, now. I'm taking a moment to look over a few other objects here to find. And while we're bringing that in, let's just do this here. I'm gonna bring up our deep space objects and select several catalogs. The Barnard Dark Dust catalog, Sharpless 2, Lynn's Bright Nebula, and Lynn's Dark Nebulas. And that's good for now. And now the things that had nothing on them before now have things labels. Alright, this guy might be a cool one to see in just a bit. Yeah. Alright, so we'll come over there in just a bit, right after we finish up here with the Gamma Sygni Nebula. Okay, so here okay, so we'll save this here. Save exactly as seen. We could actually spend weeks in Cygnus just doing studies. All right. I'm just going to take us to Deneb here for a moment. And the reason is because Deneb right here is actually an A-type star, so OBA, but it's a Roman numeral 1A. So it's also a massive supergiant star. Alright, so we're going to go west with this. I'm going to put Deneb in my crosshairs. Just a minute. I'll be heading out to the observatory again on November 2nd through the 9th. I'm going to be adding another calculation, automated calculation, to our train of calculations we're doing now. And to do that, I've got to make a specific trip. It's going to allow us to see these objects far better. And so, what the heck? Oh, I must have turned off what did I do? Hold on. That's better. Okay. So I'm gonna come down here now. Alright, now put the crosshairs on that. There we go. So I just synchronized the telescope so that now when I go look at something else over here, we will have it in our crosshairs. Let's go out here. And it's going to be down here. Right here. Yeah, there it is. Okay, we're going to go to the Cave Nebula. There we go. Okay. All right, let's I believe it's right there. I'm going to move over just a little bit and then just take a quick shot. Okay. I'll do a 20-second shot. Let's see where I'm supposed to be. There it is, right there. Okay, good. All right. Let's go back to that. All right. Hey, Fantasy, how you doing? Hey, Brandon Hill, how you doing? He says, for stars that are yellow or hotter as giants slash supergiants slash hypergiants, would that mean they are O or B in the main sequence? They were O or B. I was always curious why stars like Rigel are still so hot. That's a fantastic question. First of all, the color of the star has everything to do with temperature. The maximum wavelength that a star puts out is governed by a calculation with the color, basically, known as Wien's law. And so we would notice that stars that are O-type stars will be hot and blue. And the stars that are not O-type stars, that are B stars, they'll be more of a bluish color, bluish white. A stars are white, F stars are whitish yellow, G stars are kind of yellow, K stars are orange, M stars are red. That has to do with temperature, right? So, that said, when you look at the supergiant stars, supergiants are very large and distended, meaning that they're massive, and their massive size, okay, will mean that the fusion part is in the center. And as the star expands in size, those outer layers get farther away from the really, really hot center. So those outer layers cool off and turn more toward the red. Okay? That's why when we see supergiants, we say that some of these supergiants are red supergiants, right? But if you see a giant star that's a bright yellow star, well, that means that the star has maintained its temperature. It's at that point in its evolution where it's actually very hot, all right? Or it's a 1A or 1B star. Antares, for instance, is one of those, and it's going to go supernova, and it's red. It's cool, all right? So, but there's subgiants and giants, and the giants are just very massive stars. So they're already very big in diameter, many times the mass of the sun. So they don't have to be red. They can be white. Deneb, for instance. Okay, they can be just very massive stars. All right, so there's all kinds of characteristics of these heavier, more massive stars. 25,000. And there we go. Let me take us now to this. And I think we're underway on the cave now. Okay. So it depends on the starting mass of the star, what it's going to have for a color, and how it's going to evolve. Yep, there's the cave. Looks beautiful. So we'll let that develop a bit. Let's just color correct. And let's do process correction here just to start that process. See, after 2 frames, look, it already gets much clearer. That's really cool how that happens. I like that. So I hope you guys are all doing well tonight. I think I've been having a good time, actually. Down below here in the cave, there's another region, and I might have it just right here at the bottom, right there. That's called a Herbig-Haro object. That's actually a new, young, hot stars that are forming in there. As a young star, it's not doing fusion yet, and that's right. If you look here, okay, you see inside that red square down here. There's little 2 dots, and then it's sort of a red nebula around it. That's a Herbig-Haro object. And what those are when stars first form, they form out of dark nebulae like this. And when they form, these dark nebulae will undergo gravitational collapse, but they're also filled with this hydrogen gas. Okay, the most plentiful gas in the entire universe. Okay, the maximum amount of elements in the universe, the top-notch one is hydrogen. So as it compresses, it makes a what's called a protostar. It's very, very hot, but it hasn't reached fusion temperatures yet. But the central region is extremely hot, and sometimes these Herbig-Haro objects can spew from their north and south poles because they're spinning, aggregating masses of gas that's really, really hot, glowing and everything, but just not hot enough to fuse. Fusion requires millions of degrees, 13 million Kelvin actually, to start. And so you'll sometimes have this spinning accretion disk and this spinning material, and it might shoot some hot jets out of its north and south poles. And those hot jets give rise to things like Herbig-Haro objects or HH objects. James Webb just shot one recently, and it's beautiful. It's just stunning. Karen says, red giant, cool, white dwarfs, hot. What I learned as a kid is not accurate. Well, if you learned that red giants are cool and white dwarfs are hot, then you learned correctly. White dwarfs are the hot remaining degenerate core of a star left over after all the materials sloughed off and made like a dumbbell nebula, basically. A planetary nebula. Okay? And they're very, very hot, 40,000 Kelvin, 50,000 Kelvin. And red giants, on the other hand, again, so distended, their material is so far away from the hot central core that's making the energy that their temperature drops to like 3,000 Kelvin or even less. So it's pretty interesting. Fantasy says, Mark, have you ever considered teaching at Arizona State's online astronomy program? I think it'd be a natural. I would actually consider it. I'm actually looking for reasons to spend a lot more time in Arizona right now. Arizona is sort of like a second home. I'm very comfortable there. Except in the desert at night. When I was just there, I actually got lost coming out of the desert at night. But it wasn't a bad thing, but it was a little touch and go. Especially when I went into a wash, an arroyo by any other name. Luckily I had a 4-wheel drive Wrangler Jeep, so I didn't end up getting stuck anywhere. Wow, look at that, huh? Herbig-Haro object down here is starting to develop pretty well. It is right at the bottom, but we're focusing on this part today. So we zoom in on that. Fantasy says, learned that the hard way. My car got stuck a few times, yeah. Oh yeah, and we had some pretty cool spiders out there as well. When I was out there a few weeks ago, just a couple weeks ago, I ended up walking into the observatory building, this building right here, and as you step over the threshold to walk in the door is only like 4 feet tall. You got a duct to go in. As I stepped over, I looked down and I saw a spider web. And I kind of ignored it. And I saw a spider in there. And when I came back out to go out to the Jeep to grab some tools, I came back and looked at the spider much more closely. I squatted down looking at it. And it was the first time I had seen a black widow in real life. Oh, it's a black widow. So, they don't leave their webs, so it's not like they were a problem. So I just kept stepping over it over the course of the night. Came in, sat down, did my work. So they don't harm you, and they don't kill you if they bite you. They're not deadly. Neither are the scorpions out there, but the bark scorpion, little tiny bark scorpion, those are the most painful ones. And you'll spend a couple of months healing up from that one. But the regular scorpions, like getting stung by a yellow jacket, it's not really that bad. And if you shine a black light on them, an ultraviolet lamp, they glow bright whitish blue, and you can see them from like 100 feet away. I shined at a woodpile. I can see all the scorpions in the woodpile from a distance. This is nice. I'll change this to Cave Nebula. We are a little compromised with the moon out, so we have a little extra glow, even though we're using the special filters. It's kind of tough, so, but it's okay. This one here. Looking very pretty. Let's see if I can show you something here. So there is the tarantula that was in our observatory. Notice how big it is. They are the most docile little creatures. They would not hurt you. This one just wanted to get out of the way. And Dale, the husband of one of Tara, just reached underneath our computer table and it crawled up on his hand, and he brought it out. That's what you call someone who isn't afraid of anything. So there you go. So there's the tarantula. Very nice. Oh, the Cholla cactus fantasy. Yeah, my first visit to Arizona, my very first visit, I went for a hike from what would be the future location of SkyTour, this building, and it was back in 2014 or 2012. I was walking out in the desert, and I saw these little round balls rolling around in the wind, and I kicked one. Holy cow. You'll never forget the first time you kick a Cholla cactus. Imagine a sphere of barbs, all sticking out, all a big sphere, and when you kick it, those suckers are sharp. It went through my sneaker and into my foot. I was a quarter mile away from the house where I was staying out there. And I had to limp back to that house in this ungodly pain. And then, of course, had to endure being laughed at by the owner of the house saying, "You idiot, this is a Cholla. Don't you know you're not supposed to kick those?" Well, that was one time I ever did. Yep. And then they call it jumping Cholla because they don't actually jump. But what they do is, as you go by them, the slightest disturbance of the air or the currents around them can make them fall. And then they'll fall on you. And if they land on you, the first thing you do is don't panic. Because if you go reach for it with your hand, it's going to then stick in your hand. You need some kind of a stick or tool to help pry it away from your body. And fantasy says that the pain lasts days. It does. Yes, if you have questions, do type in all caps, or like here, Michael's asking a question. Mark, has anyone ever recommended an eclipse from the moon? Recommended an eclipse from the moon. I know you were told to use all caps. That's fair. I don't know what you mean by your question. Mark, has anyone ever recommended an eclipse from the moon? Recorded. Okay. I guess you gotta explain better. I'm sorry, Michael. Fantasy says, I feel like getting attacked by a choya is a rite of passage. Yeah, okay, I'm a desert rat now. Yeah, choyas are just no fun. But if you think of them as a life form on the planet, they are a remarkable and resilient cactus. Remarkably resilient and tenacious. They deserve to live because they've really developed a methodology with which to do it. So this is the Cave Nebula we're looking at here. Notice this area here. This it seems like it's a rim of hydrogen that's ionized. Well, what's happening is the hydrogen's ionized all throughout here, but this is black dust. It's denser in the foreground, so it's covering up the red nebula behind it. Okay, and over here, you'll notice that there is a really interesting development of materials and a look going on over here. You can see some little tiny tendrils and so forth. Now, let me see if I can draw out any more detail. May not be able to. The moon is still up. That's a little more. Yep. Pretty cool. Again, that blue is partly because the moon is adding a little bit of a blue haze to our night sky. And do you know why it's blue? You know why it's blue. We've talked about it enough. But maybe you just have to hear it one more time. It's actually because of the fact that the molecules in the atmosphere scatter the blue light coming from the sun. But wait, Mark, it's nighttime. Yes, that's true. However, it may be nighttime, but the sun is reflecting off the moon. And that moonlight that's coming back to us is sunlight reflected, and thus that light will scatter blue light in the air as well at night. That's why the moon looks like always looks like it has a blue halo around it when you look at it. Michael Hedrick says, has anyone ever recorded what we call a lunar eclipse from the moon? And what would the experience be like? Oh, I see what you're saying. Okay. Alright, great. What would a lunar eclipse look like from the moon? Actually, it might be kind of boring. Here's what you'd see. You would see the sun near the edge of the earth, and then the sun would go behind the limb of the earth, but as it does, you would end up seeing a really interesting ring of red around the earth. And that's basically sunset light as seen from that perspective. All right? And so when you look at that, you'll see this beautiful ring of red, because from your perspective on the moon, you are indeed seeing sunset, because sunset is defined as the sun going through the air along the edge of the Earth's limb. And when you're on the Earth, you only see it from a small perspective, and your horizon's very small. You don't see the whole circle of the Earth, basically, sphere of the Earth. But from the moon, you may, and see just that. So you'll have this, nearly complete ring of red around the Earth. So that's what it would look like from there. That might be pretty interesting. kind of like the annular eclipse that we just had come through, but dimmer. You would see, instead of the sunlight, you'd see the moon, or sorry, the Earth with a rim of sunset light around it, because the Earth would completely eclipse the sun, as seen from the moon, if it was dead center. Hey James, how you doing? James Dugan's with us. Daisy and Zoe Amethyst say, wouldn't an eclipse from the moon be from the Earth eclipsing the sun? That is correct. From the moon, it would be the Earth eclipsing the sun as seen from the moon. That is exactly right. Michael says, I'll buy a ticket to the lunar surface, Mark. Thanks, Mike, but I'm kind of stuck here, I'd rather look from underneath the atmosphere and not be above it. Although I have to admit, I do want to ride the Vomit Comet. That's the airplane that does that, those parabolic loops, and you go weightless for 15 seconds, and then you lay down, you go weightless again. I want to do that. I really want to do that. Trouble is, it's too expensive. And I'm certainly not going to waste money on that. I'll buy more equipment to have in the buildings for you guys. Okay, let's do this. Oh yeah. Look at that. Cave's looking really pretty. These things are becoming more defined. Alright. Cave Nebula, save. I did not put the name up, no. I was thinking about it and I figured, nah, it's okay. Alright, so let's go in here one more time. And I know where we're going to go next. The Cave Nebula is an extremely hot location. And it's really dangerous location. If we went there, it would not be a pleasant experience. At all. Alright, so let's do this. Let's say... I'm going to do that. Alright, now... the next dangerous location we're going to is right nearby. And this one is the most phenomenal looking one you'll have seen. Alright, I'll tell it to go even though I'm not quite ready. I'm gonna get out of this. And we'll join the telescope moving already in progress. Yeah, right there. Pretty. I'm going to zoom in on it real quick just now just to check my stars. Yeah, that's what I thought. Need a little adjustment. Try that. There we go. Okay. Okay, so this is another most dangerous place in the universe. Now, when we looked at the cave, the Herbig Haro object down the bottom, the protostar, very hot, very turbulent place. The cave, very hot, very turbulent place for a stellar nursery. Okay, the Gamma Sygni Nebula, very hot, very turbulent place. Less so, but we looked at the less so than say the generic diffuse clouds of hydrogen. But when we looked at the Crescent Nebula, that was also an extremely dangerous place. That's the Wolf-Rayet star there. This is a Wolf-Rayet star here. And we'll take a look at this now. First things first, though, I wasn't going to do this, but I'm going to do it. I really want to get optimum focus, so I'm going to do a focus run with you guys. So we'll see the number climb from 7 to 14 stars. 23. The more focused it gets, 25. 47. Yeah, you'll see the number climb 60 stars. Hey, Rascally Rabbit, how are you? Ricky Ricardo, how are you? Izabela says, hey, Mark, make the telescope to make a sound when you go to Arizona. It'd be so cool to hear it. Yeah, that depends on the camera and the security camera that's in the... I got 3 cameras in there. You see them right here. There's 1 and there's 2. That guy right there. And this one. But they don't have sound. So I would have to... I'd have to look at ways to get sound. And to do that, I have a pan and tilt camera in there. But that pan and tilt camera allows for sound. The trouble is, it's not able to use the Wi-Fi. Because the Wi-Fi is non-functional that far away from the main building on the property. And that's okay. Okay, now that we're fully focused, now we're going to do... let's first of all... do that. Okay, I'm going to actually go up. And then come out of here. Go to 25% just to see where I am. That's what I thought. That's perfect. Okay, great. So we're searching for our guide star. You can see up there. Numbers are going. We are ready. And I'm going to do a 25-second photo of this region. And let's stack it. And we'll have our last image in there of the cave. Which will be... This is what's really there. This is way up high. This is way up high. So we get rid of that. Okay, and it'll look like what we saw. And then we'll clear it. We already saved it. And this is the Bubble Nebula. It's a bubble, but it was created by a star that shed its outer layers in a violent outburst. And here are the outer layers coming out right here. And the star is this star right in there. It's very hot. And it's ionizing this gas out here. Again, this is a precursor to a supernova. And as we look at this, you'll see... As we look, and we just... Alright, so we can start zooming in now. This is why it's called a bubble. Look at that. Isn't that beautiful? All the way around. That's amazing. That hot central star is what's known as a Wolf-Rayet star. And layers have been puffed off of this star, and it may very well be, and this is one of Izabela's favorites, by the way. You still have it hanging over your computer desk, Izabela? She got one of our early Bubble Nebulas, which really was really pretty. It was actually taken with the telescope right behind me. Hey there, City Lights. What's going on? Nice to see you. Oh yeah, the bubble is just incredible. And I'm gonna put a notation on the Bubble Nebula that it's WR. It's actually a Wolf-Rayet star. Okay. So let's pop that up there now. Oh, what is that? Wow. That's funny. Okay. How about now? There we are. Alright, so we move that over here. Okay, so the Bubble Nebula is a Wolf-Rayet star in the process of getting close to destroying itself at some point. Wow, that's cool. This is pretty. You notice we got 8 frames stacked, and all of a sudden it started to get clearer. That's what's nice about this. It will get a lot clearer, and when we see that it gets clearer, it means that we're getting rid of a lot of the noise. We can do this. We can push this down to actually get rid of some of the noise. But that's really pretty. Look how sharp that bubble is. This is our new camera. Obviously, it's nearly twice the resolution of the previous camera. We're at 50% right now. If we go to 100% of the sensor, that's be the native resolution. This is the native resolution of it right there. And I tend to go less than that. I tend to go maybe 50% just to showcase what else there is. Because if you look around, there's a lot more going on out here. We're in a really very, very complicated region. And there's a lot more stuff down here. See that right there? That's the beginning of yet another nebula down below it called the Lobster Claw Nebula. That's fascinating too. Alright. I know Izabela. She says, wow, so pretty. It is. It's actually really interesting. But this is, again, this is a deadly place to be. This is not where you would like to go. You know, no way. This region here, okay, right in here, this right here, this bubble that we're seeing there, generated by that star right there. That was a very, very hot young star originally, maybe roughly 10 times the mass of the sun, maybe more. And it blew off its outer layers for reasons that we don't know why Wolf-Rayet stars do what they do exactly. We have ideas. But you'll notice this beautiful bubble here. It's really uniform. You can see the spherical appearance. And then you see this stuff out here. This is the additional material that was ionized by this hot star. I'm going to say that this stuff right here is what came from the star. This I don't think came from the star. I think this was just ionized debris in the region, but I have to check on that. That's crazy. Let me go back in the corner now. There we are, back down here. Yay. I want to thank our patrons so far. We've got John P. We've got Isabel M. Ollie B. Chief McCyber, Vera C. Ronald T. Martin W. Raymond B. Cindy M. Susan W. Diane H. And JSCO 77. We'd like more patrons. We need more to survive. We got a lot a lot of equipment that we're adding. We want to make sure that we can continue bringing all this to you. So anything you can do to help, that'd be great. But you can visit, if you want, just visit skytourlive.org. And up at the top, you can see our Patreon, and you can see other places to go. You can get prints of all these things, framed on canvas, on metal even. You can also buy lots and lots of really cool swag available at the Etsy store called Sky Tour Shop if you want to go there and check it out. It's on Etsy. Izabela put up our Patreon page. Thank you, Izabela. That was very kind. You know, I gotta tell you, I was getting tired a few minutes ago, and then I realized, wow, look at this Bubble Nebula, and I'm not tired anymore. All right, Michael Hedrick says, Mark, do you know what Bortle scale of dark sky William Herschel would have enjoyed? That's a good question. I would guess that he was probably a 1 to 2 where he was. But there might have been some light pollution from some of the lighting around there. Now, keep in mind, it didn't have the same lights as us. And it didn't have the reach. So, it was probably exceedingly dark. I would love to check it out. I would love to be in New York City when you could see Milky Way over your head. Now, at that point, the Milky Way was the same as it's always been, but the New York City would have been, coaches and gas lamps probably at some point that, again, didn't have the reach. Like you have now with LED lighting and so forth. They can reach like hundreds of feet, and those gas lamps did not have that reach. The big problem then was coal fires for energy. Coal fires really polluted the night sky and added tons of pollution. Remember London fog? Yeah. In part because of coal fires. Christmas is coming, Izabela says. Lots of cool things in our Etsy store. We have almost 100 products up there. Fantasy says, best place I ever saw the Milky Way was the band coming out of Mount Whitney's Peak from the foothills. Oh, wow. I can imagine that was beautiful. Izabela, this comment is especially for you. If you take a look at this, we've never seen this kind of detail in the bubble before. We've never seen this kind of detail. And the reason it's for Izabela is because this is one of her favorite objects. Look at that. I'm going to drop our level down to reduce some of the noise again. Wowee. That's looking great. Alright, so now I'm going to just back out. Okay. Let it go where it wants to go. That's just there. That's what I expected. Okay. And let's see what else there is. We're going to use this histogram over on this side. Punch it. And now you can see as we back out. I mean, it looks noisy and nasty. But you actually see what's really in this picture. You can see the Lobster Claw Nebula beginning here. You see another one over here. Okay. You see this beautiful cluster up here, open cluster. And then you have the bubble. Really nice. So we'll come back to bringing that out. Drop down. Ah, yes. Wow. Yeah, the Christmas tree nebula is going to be beautiful. Izabela mentioned she wants one of the Christmas tree too. If you go on our Etsy store at SkyTour Shop, you can actually find the Christmas Tree Nebula with all its detail on a big 80-inch by 60-inch fleece blanket. I actually saw that in real life. And a lot of these products I would never do unless I actually could get them and look at them myself. And it really is just astonishing. Really, really pretty. I also have sneakers that have some of our stuff on it too. The sneakers themselves have printed imagery on it. You can get bathing suits, clothing of all kinds out there. It's really cool. And we're selling on Etsy right now, but we'll be on Shopify and we'll be online at Walmart here before long. We have to try and get we have to try and build up the amount of revenue for what we're doing, because now that we got a serious engagement here with these telescopes, there's a lot of work, you know. Cindy Murphy has that blanket I was just talking about, and there she is mentioning it, I think. Cindy Murphy says, "Beautiful blanket. I'm wrapped in it now." I know. I want to be wrapped in it too, Cindy. It just feels like it's chilly here in Connecticut today, and I don't like the chill. I have a heater running right next to me. Look at that. Okay, we're gonna save the Bubble Nebula here. Gosh, that's beautiful. Wow. Okay. And let's back out here for just a minute. Alright, so here's what we're going to do now. We're going to go down and to the right, and we're going to capture this Lobster Claw Nebula that's right down there that you can't really see. Okay, so we saved it. It's up there. And so now we're going to go and check out the Lobster Claw down below. Let's bing, get out of there. We don't need that. Okay, so now here we are. Okay, there is the bubble. Let's go here. So we're going to go up. Okay. And then we're going to move over. Okay, we're going to do a quick 30-second shot of that. Or no, sorry, a 20-second shot of that just to see. I'm not waiting for our guide star. I don't need it. I just want to quickly grab this. So we're going to clear this. And wait until we see what's happening here. Hey, Lewis, how are you? Thank you for dropping by. Let's see where we are here. Wow, look at that. Alright, so we got a little more to go, but that's where we're going. Nice, so I'm going to put that right there. Or actually, no, I'll move that here. Okay. Nice. Okay. So that guy, we're going to move up just a little more. Okay. Head westward. Okay. This nebula is really interesting. Hey, it's Marianne Robb. Hello, Marianne. How are you? Oh, wow. I was just telling everybody, Marianne, that you're out in Ogden, Utah at KGRA's headquarters. You want to tell people what you're doing? Okay. Let's do this again here. 25 seconds. Now come into live stack. And now this will be up farther. We'll clear it. Marianne, of course, is on the iDetective show on KGRA. She's also in UAP PD. She formed the UAP PD with Dave Rich, another good buddy and law enforcement guy who's fantastic. And then KGRA Digital Broadcasting, that's what the DB stands for. She's hanging out with them. Okay. Let's just do that. Look at that. So there is our nebula. You're going to see, it's called the Lobster Claw Nebula because it's got these two claws, like pinchers. It's pretty cool looking. I like that. E.T. E.T. What you gonna do? What you gonna do when Marianne comes for you? City Light says, it's the claw of Zoidberg. Oh no. Hey, look out, won't you? The claw of Zoidberg. Yeah, Marianne met Jimmy, Eric, and Warren, who are with KGRA. Really cool guys. I got a tour of the studio today virtually. Marianne took me around, which is neat. Okay. All right, that's the lobster claw. I mean, there's more that's down below, but I didn't want to lose the claws. Yeah, I'll be teaching in the boot camp too out in Arizona. That's another reason I'm going. Marianne's house is like Grand Central Station. She puts everybody up. Oh yes, Michael, that star cluster at the upper right. Let's go check that out. Oops, I don't want to be here. Yeah, I do. Okay. That's the salt and pepper cluster, I believe. Is that not the salt and pepper? I think it is. No, wait a minute. I'm upside down. No, I'm actually down here. Sorry. Alright, so I'm here. There's the Lobster Nebula. And that's the Dormouse cluster that we're looking at up there in the upper right. See, this is upside down. So it's in the upper right. Alright, and actually, we're right there. So in the upper right, we have the Dormouse cluster right here. Isn't that cool? Izabela, you better be careful. I told you. We're going to bring you here. Oh, Marianne's letting on some secret information. Yeah. Yeah. I've got the design figured out for how the telescope is going to open and close at the new building. It's an enclosure that's going to be like this, and it's just going to open like a flower petal and drop down, and the telescope will be exposed to all the horizons. Actually, we'll be able to zoom in and focus on the top of a saguaro cactus 2 miles away easily enough. So it'd be kind of cool. And Marianne's not kidding, Izabela. If you come out, you go to Arizona, you've been in California, you know. There's a place for you. You just can't stay in the room I rent at Marianne's. I have all my clothes there. Or if you do, I gotta knock and you gotta let me come in and get my clothes. Lewis says Marianne is a woman in black. Actually, she was in Roswell in 2019. There was a parade and she was dressed all in a black outfit. You couldn't even see her. But she had an alien head on, if I recall. No, Izabela, they won't run away in horror. They will greet you with open arms and then come visit you at night in your bed. And say, "Come with me. We're going to take you on a trip far across the sea." Oh yeah, the John and Stan are the Navajo Rangers. All good friends. Yep. Galaxy Defender, that's right. Men in Black. Yeah, well, this is cool. Oh, Vincent, I don't think I said hi to you tonight. I'm sorry. Vince Giglio, how are you? Oh, thanks, Marianne. She says, we'll just put Mark out in the travel trailer and you can have any bedroom you like. No, Izabela, if you come out, you're going to go scorpion hunting with me. Oh, yes. You know why? Because for every scorpion we capture alive, we get 10% off at the Ace Hardware in town. And you put them in the terrarium with all the other live ones. That's what we do out there. Ask Marianne, she knows. Hey Gladys, how are you? Yeah, Daryl's not with us. Yeah, look at that. That's really developing well. That's 20 shots. We'll save it right there. Izabela, if you use an ultraviolet light, black light, on a scorpion, they light up bright bluish white. you can't miss them. You can see them from 150 feet away. No lie. So you won't have any problem. You won't get stung by them at all. Although Marianne almost got stung the other day because she was putting the cover back on the outdoor furniture, and a silly person didn't notice that there was a scorpion inside the fold. She didn't get stung, but she got close. Isn't that right, Marianne? Let's zoom in on one of the claws. Okay, see what this is now? This is, if you look at this is oxygen 3, doubly ionized oxygen. That's what the greenish color is. And it's rimmed with a little of the red hydrogen alpha emission. And then we have this really intense hydrogen alpha emission right down here. Very, 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 very bright region. Now it's possible that we're looking at all of this through a layer or veil of dust. And that this spot is one where there is not a lot of dust, and so it shows through very brightly. Actually, Izabela says, she says, now I imagine the desert lit by blue light and thousands of scorpions glowing and crawling around. Actually, that's not true, but what is true is if you go to where we do the boot camp, which is called it's a park called Weaver's Needle out there. If you look in the parking lot and you shine the light in the parking lot at night, you're going to see thousands of blue splotches all over the ground where cars ran over scorpions over the years, and the glows are still there. That's really cool. Yeah, Needle Vista. Yeah, that's right. Needle Vista is the name of the park, and it's in Needle Vista where you can see Weaver's Needle, which is the rock formation like 3 or 4 miles further down the range. Thanks, Marianne, for the correction. Nah, I'm not freaking out, Izabela. And Lewis, the scorpions are not poisonous. They're just annoying. Like getting stung by bees. You know, the bigger scorpions are actually less of a problem than the tiny ones. The small scorpions, known as the bark scorpions, those will feel like an Asian hornet sting, but the bigger scorpions are going to feel like a yellow jacket sting. You know, that's how I've heard it characterized. So the Asian hornets are like this big, and they have big stingers. So, that's the bark. The smaller scorpion actually hurts more, and the recovery's longer. Okay, we're gonna go one more image here, and then we'll have enough to complete this beautiful lobster claw. Wow. I don't remember this red thing. I'm going to have to consult the last lobster claw and see if this red nebula was in there. I don't recall that. Okay. All right. All right, that's great. So let's come out of here. There it is, the whole thing. A little more down below. Let's go here. So we went from the Bubble Nebula down south. That's actually south because we're almost directly over the pole right now. That's the Northern Lagoon, I believe that's called. Yeah, Northern Lagoon. Or the Brain Nebula. It's small. Okay. Let's back out of this a little bit. Yes, sirree. Okay. Okay, and we'll check out our final evening object here. Louis Toss says it looks like a red supergiant. It does, indeed. Dean Bostador, how are you? Yeah, you don't have to worry about mosquitoes out there anyway. Okay, so this guy here. Alright, we're gonna go this way. Okay, and then I'm gonna just do a quick one to make sure that I'm where I want to be. Placement shot. So Lobster Claw will be up on the server. You can see how much more there is in there. Okay. Let's make sure we're in the right location. Oh, yes, we are. I'm just going to move us a little bit, and then we'll be fine. Okay, now we go up. Okay. Okay. Marianne's flying back. Okay, I won't freak out Izabela, Marianne. I don't want to freak her out. I want her to come. I want her to come out here. I told her we'd orchestrate that too. Okay. Let's do this beautiful region. Talking about dangerous spots in the universe. And this is another one. These are regions that are hot, but we're ending on one that's actually dangerous. However, there's a possibility that it could also show us that there's a future for life in this particular region. All right. There we are. Alrighty, so here is this beautiful nebula called the Elephant's Trunk Nebula. Right, and I will just let it develop a little bit. Right, and we'll call this Elephant's Trunk. Oh, Sam, did you go to bed? Or is Gladys going? Okay, Gladys is. Thanks for coming, Gladys. We'll talk to you again. This is an amazing location, and I'll show you why, because we're going to look in here. when it develops a little more. This is a region you do not want to be in. Okay, so there's a lot of gas and dust here. You can see a lot of it there. Let me see if I can increase the contrast. We only have 4 stacks, so it might be a little tough. Let's try it. Okay, this may work. Alright. Okay. So right in here, it'll become clearer too. There's this region, this nebula, and in the middle of it is a star. And around that star is this open cavity, this open, like, donut, basically. This is the elephant's trunk. This is what's called the elephant's trunk. But that round opening is round and open like that because the star inside has, with its radiation, pushed gas and dust away from itself. You know, stars want to be left alone, you know. Yeah, this is going to be a pretty one. Our corrections are very small, so that means that this is just a... this is going to be a beautiful image. So, as we move back out, you'll notice this dark area up here. This dark spot up here, this is dust, that is micron-sized dust particles, also molecules of carbon and silicon together. And those molecules will form the basis of the cloud. And they're littering the galaxy with all kinds of material like this because of this process that's ongoing in the universe where stars are born and die. When they die, they create supernovas or planetary nebulae, and in the end, all the material that a star is made of gets expelled back to the interstellar medium, plus stuff that it made in its core. Because the reason that you're here is because of the star stuff that you are made of, and the stars made all of that, all of those elements that you're made of, the phosphorus, the calcium, the magnesium, all that was made in the heart of a star or in a supernova. And it's really kind of fascinating to ponder that everything you're made of was once made in the heart of a star at many tens of millions of degrees, or above 100 million degrees. So that is a pretty, heady thing to think about. Every element in your body manufactured through nucleosynthesis. So the Kelvin scale is a temperature scale, and Kelvin is the actual replacement for the word degrees. So when we say 100 million Kelvin, we mean that the temperature scale is the Kelvin temperature scale converted to Celsius, if you want to talk about it with Celsius, and then convert it, and then it'll be in degrees, and then convert it to Fahrenheit, which would be in degrees as well. So the conversion for Celsius is simple. Okay, minus 273 Celsius is absolute zero. So it's basically 273 is the fudge factor to get to Kelvin, to get to any Kelvin value. And for Fahrenheit, it's like minus 400 and change to get to absolute zero. Look at this. This is really pretty. Let's see what it thinks it wants to do. It wants to draw it out. Yeah, look at that. Wow. Really makes this stand out when it does that. even though it's a little bit dimmer, it shows the detail in here. You can see these strands, which will come in a second. Look at that. Beautiful stranding. You can see how that cavity is now here. You can actually see the illumination inside the cavity where the star has ionized some of the hydrogen gas that's in there as well. It'd be very cool to go zipping through there. Okay, let's see here. Okay, the distance to this in here is about 1,500 to 1,600 light years. Izabela says, where is the star my carbon came from? That's a good question. I imagine your carbon came from many stars, actually. Not just one. Amazing to see this stuff just floating out here like this. And you say, what else is there? We can just punch it up with this artificial enhancement here. You can see what else is in here. Look at that. So there's dark nebula up there. That's a cold, dark region. And it's very, very dense relative to, say, this region of stringy, dark nebula. And this region here of hydrogen gas mixed with dark dust. Okay, I mean, look at that very sharp delineation there. But this is the densest part of this region. And by dense, I mean that in a cubic centimeter, instead of having 10 to the 19th atoms, like we have in our air, roughly, you might have 30,000 atoms. So that's a far cry fewer than 10 to the 19th. But, again, for an interstellar location, that's actually dense. Obviously, the stars are denser. But the nebulae are usually only between 30 and 3,000 or 30,000 atoms per cubic centimeter. And that's, space like that. So let's go back to this. It'll get dim for a moment. And then we can start to work this up the chain until we get to that magic spot, which I may have just hit. Because I want you to see here. Okay, this is the elephant's trunk region we talked about. This is called the caravan because it looks like camel humps. So the camel humps are the caravan as a feature. I mean, obviously, they're not really camel humps, but you get it. Before I went out there last time, I tried to shoot this object, and these two stars were not round. They were actually elongated blobs. It looked like comets, little tiny comets. It was out of alignment, so I went out there to align it. And Marianne and Tara tried to align it, but it didn't work. It wasn't their fault. They had no experience doing alignments. But they tried, and because of what they did, it made it easier for me to do it, and it took me only an hour to fix it. Look at that, it's beautiful. Wow. This is going to be a stunning shot, guys. Even with the moon. Yeah. So the promise of life then lives in these dark regions. And I mentioned that before. These dark regions are my hot button because you come from these dark regions. Everything that is in your body at one point came out of a dark region like this right here. And this is a very complex region full of chemistry of different types, and elements of many different types, and flavors, and variations and densities. Izabela and City Lights are having a moment. You talking about the black ball here? Is that what you're saying? Shot out of the elephant's trunk? Lewis, no, these are not protostars. These are actual stars. These stars winked on a long time ago. So those aren't protostars. Alright, protostars are stars like we saw in the cave, where down below I talked about those Herbig-Haro, Herbig, and then Haro, Herbig-Haro objects. And I mentioned also the James Webb Space Telescope just captured a beautiful Herbig-Haro object with beautiful north and south polar streamers of energy coming out, because let me tell you, these things are very energetic when they're young. C&D boy, what's going on, man? This will pop in here in a sec. Look at that. Okay, we'll save it with 30. Very nice. I'm actually very pleased with how it's all performing tonight. It's doing very well. Look at the detail now. You see the detail right in here. Look at that. That's going to be richly discernible when we actually process that. Okay, well, there we go. That's 33 images. And that's what we got for tonight, guys. I hope that you're having a good time, or had a good time with us tonight. I hope that you guys will come back again. I know you will. Again, if you can, join us here. Go check out the SkyTour shop at Etsy, or go to skytourlive.org. And skytourlive.org is our portal to all this. You can actually find our channel, come here. You can find our Patreon. You can find our store. And a whole bunch of information about us as well. So you guys have a good night. And I will see you on the flip side. And if you have any questions about tonight, feel free to send me a message. You're more than welcome to write me an email. Let me see where that is. I know I have an email here for you guys. Here it is. You can find me here. All right. Let's just a second. Email. There we go. It didn't want to work. Okay, I'm trying to capture it. Oh, I see why. Sorry. That's my email if you want to talk to me directly and you want to send a message. It's mufonanalyst@gmail.com. You can also reach me at contactskytour@gmail.com, which will be the message or email I'll put up in the future. Anyway, there you go. If you guys had a good night, let me know. Make sure you give me a thumbs up down there and pass it along to all your friends. And for those of you that were my friends on Facebook, know that I was hacked, and I want to make sure that you understand that I've committed to the new Facebook profile. So I'm not going to pay a ransom to some Indian hacker to get my old site back. So this site is protected better. And it was Facebook, not Sky Tour Livestream. So we're good. So if you were a friend and are no longer, send me a friend request, will you? And let's get back on the road to getting my 4,800 friends back. All right. Have a good night, guys, and I will talk to you later. Normally, this is like just one more, but this was the one more. So, have a good night, guys, and we'll see you later.